Hey everyone, and welcome back to The Explainer. So today we are tackling an absolute cornerstone of modern electronics, the tiny little device that essentially birthed the digital age. If you've ever looked at a complex circuit diagram and felt a bit overwhelmed by those little three-legged symbols, you are in exactly the right place. We are going to completely demystify the bipolar junction transistor, or BJT. My goal here is to turn dry semiconductor physics into a really dynamic logical story. By the time we're done, you won't just be memorizing what a BJT does, you'll understand exactly how it works from the inside out.
Okay, let's dive into this. Here is our cognitive roadmap for today. First, we'll meet the BJT. Then we'll look at the anatomy of the transistor, follow the electron journey, get configurations explained, read the characteristics, and finally cover biasing and stability.
Section 1. Meet the BJT.
Now, what's really interesting about this slide is exactly where BJTs sit in the broader, overarching transistor family tree. Notice how transistors generally split into two massive camps, right? You've got your BJTs and your field effect transistors, or FETs. And as we move down that left branch, the BJT family splits again into NPN and PNP types. Now, while FETs absolutely dominate modern digital chips, the BJT is a total classic. It's fundamentally a current-controlled device, and honestly, understanding it gives you the absolute best foundation for grasping how any electronic amplification actually happens.
Let's actually break down the name itself because, well, engineers are nothing if not literal. Bipolar tells us that the current relies on two distinct types of charge carriers, electrons and holes, which are literally just the absence of an electron. It takes both of them to make the magic happen. The word transistor implies the transfer of a signal from a low-resistance input path over to a high-resistance output path. Simply put, a tiny current at the input basically acts like a valve to control a massive current at the output.
Section 2. Anatomy of the transistor.
So what does this internal valve actually look like in the real world? Well, we have two flavors of BJTs, NPN and PNP. You can kind of think of them as a semiconductor sandwich. An NPN transistor has a single layer of P-type material squished right between two N-type layers. A PNP is the exact reverse. Now, when there's no external voltage applied at all, when they are unbiased, free electrons and holes just naturally diffuse across those junctions and recombine. This creates what we call depletion layers, which basically act like natural built-in walls right at the junctions. Now, to actually interact with this sandwich, we connect three metallic terminals, and each region is engineered with a super specific job. First up, the emitter. It's heavily doped with charge carriers, and its sole job is to aggressively inject them right into the middle. Next is the base, that middle layer. It's very lightly doped and incredibly thin, specifically designed just to pass those carriers along. And finally, the collector. It's the largest region by far, and its whole purpose is to essentially catch or gather up all the charge carriers that make it across.
Section 3. The electron journey. All right, now that we have our static map down, let's treat these electrons like the real protagonists of our story here. Let's move to and see how this builds when we actually apply a voltage to an NPN transistor, pushing it into what's called the active region. Step 1. The emitter forcefully injects a massive amount of free electrons across the barrier and into the base. Step 2. Because that base is so incredibly thin and lightly doped, the electrons barely have any time to stop and recombine. They just shoot right through. Step 3. The powerful voltage waiting over on the collector side acts almost like a giant vacuum, gathering almost all of those free electrons up.
And this brilliantly illustrates exactly how extreme this difference is. Just look at that massive vertical arrow pointing up from the emitter, blasting straight through that tiny base region and then expanding out into the collector. That right there is our primary flow. But now look over at the base lead on the left. You see that tiny horizontal arrow? That's the minority hole current. That represents the tiny little bit of recombination actually happening in the base. It's essentially a tiny trickle controlling a raging river. Which leads us directly to the fundamental math of the transistor, the golden rule of BJT currents. The total current leaving the emitter, IE, is always exactly equal to the tiny base current, IB, plus the massive collector current, IC. Really try to lock this equation into your memory. It proves that electrons don't just magically disappear. Every single charge carrier injected by the emitter is perfectly accounted for.
Section 4. Transistor configurations explained. So how do we actually wire these tiny components up in a full circuit? Well, since a transistor has 3 terminals, but our standard circuits need 2 inputs and 2 outputs, one terminal always has to be shared, or common, to both sides. First up is common base, where the current gain is represented by alpha. Now, the current gain here is actually less than 1, but it completely makes up for it by delivering a really high voltage gain. Second is common emitter, with a gain we call beta. This one is incredibly popular. It's the most widely used configuration out there because it offers this fantastic balance of voltage and current gain, making it a truly incredible all-around amplifier. And finally, common collector, representing a gain of gamma, which is very often used as an emitter follower or buffer.
Before we move on, I want to give you a brief but super strategic reminder. IE equals IB plus IC. Look, if you flip through engineering textbooks, you are going to see a dizzying array of equations converting alpha to beta to gamma. Do not let it intimidate you. Every single one of those complex algebraic relationships stems directly from this one simple truth. The total emitter current is simply the sum of the base and collector currents. That's all it is.
Section 5. Reading transistor characteristics.
Okay, let's shift focus to how we actually predict and manipulate what a transistor will do. Because our BJT sandwich has two specific junctions, the emitter base and the collector base, we have 4 possible ways to apply our voltages by toggling each junction between forward and reverse bias. This table reveals those 4 distinct operating states: active, saturation, cutoff, and inverted. Literally, just by changing those external voltages, we push the transistor into completely different modes of physical behavior.
So the crucial point is exactly how we utilize these regions. When it's biased into the active region, the BJT acts like a beautifully smooth valve. It becomes an amplifier, where the output is strictly controlled by the input. But what happens if we push it to the extremes? In the saturation region, it becomes a fully on switch, maxing out the current entirely. And in the cutoff region, with both junctions reverse biased, it acts like a fully off switch, blocking the current completely. This amazing dual nature, smoothly amplifying a signal or snapping completely on and off like a digital switch, is the absolute bedrock of modern electronics.
Section 6. Transistor biasing and stability.
Now, getting a transistor into the right region is honestly only half the battle. Keeping it there during operation is the real challenge. When engineers talk about biasing a circuit, what we mean is applying very specific, steady, external DC voltages to those terminals. The goal is to establish a rock-solid operating baseline, which is known as the Q point, or quiescent point. The VBB and VCC batteries you see here, they are setting up those precise baseline conditions. That way, when a real, fluctuating AC signal, like a voice coming from a microphone, hits the base, the transistor is already awake, totally stable, and ready to react predictably.
But why does this matter so much? Well, because the real world is incredibly messy. Without proper biasing, our circuits would be completely chaotic. A transistor might drift right out of the active region, severely distorting your amplifier's output signal. More importantly, semiconductor materials are notoriously sensitive to temperature. If a BJT gets hot, its internal leakage currents increase dramatically. This can actually trigger thermal runaway, where the transistor basically destroys itself. Proper biasing circuits lock that Q point in place, maintaining vital stability even under severe temperature and supply variations.
Which leaves us with this final mind-boggling thought. We've just spent this entire explainer looking at the delicate electron flows, the microscopic doping layers, and the incredibly precise mathematical biasing required to make just one single bipolar junction transistor operate perfectly. So if it takes this much physical precision to manage just one, how on earth do engineers manage the flow of literally billions of them packed tightly onto a chip the size of your fingernail to power the massive computing systems we rely on every single day? It's an absolutely fascinating problem of scale. Thanks so much for joining me on this explainer, and keep questioning how the amazing world around you actually works.